Hello students, welcome to JCE Connect series of lectures. So in previous lecture we have solved some of the examples on curved vanes considering stationary as well as moving. So in this particular lecture I'll be taking one more typical case, that is a jet striking a moving curved vane tangentially at one of the tip and leaving at the other. So in previous lectures and all, we have taken a moving case also, where the jet was striking at the center and the vane was moving in the direction of jet, and there the vane was considered placed symmetrically about the x-axis, and here the vane is being considered unsymmetrical case, and the jet is striking tangentially at one of the tip. So this is the case where I'm considering in this particular lecture, and this case to be solved by using a velocity triangle concept. So this velocity triangle concept which can be used mainly in turbo machines. So what are turbo machines? A turbo machine describes, that is machines that transfers energy between a rotor and a fluid, and which includes both turbines as well as compressors. While turbines transfers energy from fluid to a rotor, whereas a compressor transfers energy from rotor to a fluid. So in these turbo machines, they could be a turbines or a compressor to analyze the fluid force, or if you want to calculate the force exerting by the fluid or work done by the fluid. So we have to use the velocity triangle concept. So what do you mean by velocity triangle? A velocity triangle or a velocity diagram is a triangle representing the various components of working fluid in a turbo machines, and velocity triangle may be drawn for both inlet and outlet sections of any turbo machines, and the vector nature of velocity is being utilized in this particular concept. The vector nature of velocity is being utilized in these velocity triangles, and the most basic form of velocity triangle consists of the absolute velocity v1 and the blade velocity, that is u1, and the relative velocity vr1. And as we know from the previous lectures, so a jet was impinging water on the blades like this. So this is the rotor or impeller of the turbine, since we are considering the turbo machines, and the jet is impinging water on the blades. These are the blades mounted on the impeller or a rotor, and the impeller is in turn coupled with the shaft. When the jet strikes the vanes, this vane starts moving in the direction of the jet. Okay, in the direction of jet. So then next again this will move forward with the velocity u. Then the next blade will come and stand before the jet. Again that vane also receives the force by a jet, then that also moves forward. Then the third blade will come and stand before the jet, that also receives the force and moves forward, and this will continue. Hence the force is being transferring from jet to the vane to the impeller or a rotor to the shaft to the generator, hence the production of electricity. Then for the analysis of forces or the analysis of velocity, how the velocity is being changing at every stages, because before coming out of the nozzle what was the velocity, then once it comes out of the nozzle what could be the velocity, then the moment it hits the vane or the blade what is the velocity in the blade passage, then when it is coming out of the vane what could be the velocity, and how it can be represented. So that can be represented by drawing a velocity triangles at inlet as well as at outlet. Okay, at inlet as well as outlet. So and typically, as I said, this velocity triangle consists of absolute velocity, that is 3 component, and the blade velocity as well as the relative velocity. Then as you know, see this is the vane. You can say it is a one blade. So I have taken one blade I am taken. So here one blade I have taken. So what happens here, when the fluid entering the vane, see this is jet is striking tangentially like this. This is the vane, and the vane starts moving in this direction. So as the fluid entering the vane and it glides over the surface like this, it will glide over the surface. As it is doing like this, there is a change of momentum. Either there is a direction, or that is either there is a direction of fluid, or both magnitude and direction of fluid are changes. Means here you can say a nozzle, the jet is coming out of the nozzle. This is the nozzle, and from the nozzle the water is coming out with a very high velocity, a jet. It produces a very high velocity jet. When it enters into the blade passage, okay, it will come out with the velocity v, and this is also moving, but it enters with relative velocity. Okay, so how that can be that relative velocity or the absolute, this is called absolute velocity. Then next comes, this is the blade velocity, then next comes the relative velocity. How these all can be drawn by using the velocity triangle concept, we will see later. So as it enters into the blade passage, what happens here, the momentum of the momentum, either there is a direction of the fluid, or both magnitude and direction of the fluid are get changes. So there is a change in the momentum of the fluid what we get. Then water will be passed through the nozzle. As we are passing through the nozzle, when it comes out of the nozzle, it will come out as a very high velocity jet and impinges on the blade. When it impinging, it will move over the blade passage, and there is a change of momentum what we get. Then the fluid momentum that will be transmitted to the blade passage, because water is gliding over the surface, and the fluid momentum that will be transmitted to the blade passage, that is or some amount of force will be exerted on the blade passage, and the blade will move in the forward direction, in this direction. Then another blade will come and receives the force, as I explained earlier. See here again, in this case, as the fluid is striking the vane, then the water is gliding over the surface like this. So as the fluid is gliding over the surface, there is a change in the momentum, either the direction of the fluid or both magnitude and direction of the fluids are get changed. And because of the change in the momentum, this blade receives the force, and as it receives the force, then it starts moving in this direction. Then again the next blade will come and stand before the jet, that also receives the force. Again the third will come and stand before the jet, that also receives the force. So this continuous rotation will go on, and ultimately from the blade the motion will be transmitted to the disc and shaft. That is, this is the disc, we can call it the disc or a rotor or impeller, and the motion will get transferred from the blade to the disc and disc to the shaft. Then from the shaft we will get the output in the form of electricity. That is how it works. And if we have to do some analysis, we have to see how the fluid velocities are being changing at every stage, and what are the different components of the fluid velocities. uh, that component can be drawn in the form of velocity triangles, and these velocity triangles are being used to find the force exerted by the jet and work done by the jet. And here we have drawn the velocity triangles like this. So like this, you have to draw the velocity triangle like this. So initially first you look at the inlet velocity triangle. So we have drawn the section of the nozzle here. You can see here we have drawn the section of the nozzle like this. This is the pipe. This is section of the nozzle. From the nozzle the water is coming out the very high velocity and hitting the blade. So here the blade is placed. We have taken one blade. Okay, so we have taken one blade and we are analyzing the fluid velocities here. Okay, so we have drawn the section of the nozzle. Through the nozzle, with some velocity of the the fluid is coming out. That velocity, let us take it as a v1. Since this is happening at inlet of the blade, so let us consider the velocity also v1, that is for inlet velocity triangle. Okay, so this v1 is nothing but absolute velocity of the jet, and that is the nozzle is fixed. Here the nozzle is fixed, and the velocity with which the fluid is coming out of the nozzle, the velocity with which the fluid is coming out of the nozzle is called as absolute velocity of the fluid at the inlet, and this is denoted by v1, and it makes an angle alpha with the horizontal or to the tangential direction, See, in this case, if you take, see, as we have taken the jet in horizontal direction, but actually if you take the jet is striking in this way, so this is the jet and this is the tangential direction. Tangent, if you draw here, it becomes a tangential direction. So it makes an angle of alpha with the tangential direction or with the horizontal. Then next, this velocity v1 making an angle alpha with the tangential direction or with the direction of motion of wave. So here, look at this figure here. The jet is striking in this way. The vane is moving in this direction. Okay, the vane is moving here. From this diagram, we get VR1, that is the relative velocity of the fluid. There is a relative velocity of the fluid, and that means with this velocity it comes inside the blade passage. Means here from the nozzle, the jet is coming out with a velocity v1. This is called absolute velocity, but the jet is not striking the vane with this velocity. This will strike with a velocity called VR1, that is relative velocity, because the vane is also moving here. Okay, the vane is also moving and the jet is also moving. Both are moving. Then we have to take the difference of these two, that becomes relative velocity, that is represented by this one. Okay, so this is absolute velocity and this is the vane velocity. Just to shift this to here and keep here, this becomes u1. Whatever u is here, the vane is moving, just it is kept here. So like this, see, I'll draw here. So this is the jet velocity v1 and this is the vane velocity u1. Okay, then the difference of these two, this is what we call as the vector difference of these two, that is we get relative velocity v1 minus u1 vector nature. Just you shift there and I'll draw next like this. This is v1, the same magnitude and direction. I'll shift here and keep here. This will become u1. Then this will be, this represent VR, relative velocity. So this is what we call as a velocity triangle. This is the resultant. So this is called a resultant, that is this is joined by head of that is a tail of relative velocity is joined with the head of absolute velocity. Okay, this represents the relative velocity and this entire triangle what we call as a velocity triangle. Then next, this one, so we have placed the tail of vector v, like here as I said in this one, the tail of vector v, this one, the tail of vector v, this is the tail. They take this as a tail in vector and this is the head. So place the tail of vector v at the head of the vector u. So at the head of vector u, that is u equal to that is a plate velocity and v equal to the absolute velocity. Then we have to construct the velocity triangle like this. Actually it is like this, v1, then this will be u1, then the third will be like this. Okay, this will be what, vr1. So what I have done here, just shifted this one here, same magnitude. Then you have to join this one. This will be VR1. This is V1 and this is U1, this is VR1. Okay, like this. Then from this diagram, as I said, that VR1 is the relative velocity of the fluid. That means with this velocity it comes inside the blade passage and moves through the blade passage. In the blade passage, so as it is moving with this velocity in the blade passage, there could be a frictional resistance in this blade passage. There could be a frictional resistance. Due to that, when the fluid comes out of the blade, it may have a different relative velocity, that is VR2. If you take this is a VR1, then it glides over the surface like this, and it comes out with this velocity. This is called VR2. This velocity is called VR2. And though, look at this figure, though the blades move in a circular path, these blades will be moving in a circular path. This is not moving in a linear path. Though the blades are moving in a circular path, but for a small amount of time, if you consider a very small amount of time with which it is in contact with the fluid, this blade with which it is in contact with the fluid, we will assume that it is having a linear motion like this. We'll assume it is having a linear motion in the direction given by the arrow, that is this one, in the direction given by the arrow. This is given, that is U1, and it is not having a linear, actually it is not having a linear motion, but for a small amount of time during which the fluid jet strikes on it, it will be having a linear motion. Then it takes the rotary motion. Okay, I hope you understood this one. I'll repeat, though the blades move in a circular path, actually it will be moving a circular path, but when we draw a velocity triangle, we are taking in a linear path. So initially for a small amount of time, a very small amount of time, when it is in contact with the jet, it will first move linearly. The moment the jet strikes, it will move linearly with velocity u1, then it takes the rotary motion actually. Okay, so here we have drawn, this is a v1, then this is the motion of blade, then this motion of blade we have shifted here and kept here like this. Then the difference of these two will give you the relative velocity. Then the triangle ABC is a inlet velocity triangle. Okay, triangle ABC is a inlet velocity triangle. Then as the jet is entering with a relative velocity VR1, and assuming this blade passage is having a very smooth, there is no any frictional loss here, and if at all the frictional loss are present, and that whatever the jet is coming out of the blade passage, it will come with the different velocities. Okay, so here I am considering the inlet velocity, that is a relative velocity VR1, and the outlet velocity is VR2. Okay, again the blade is taking a linear motion. Again at the outlet also you have to take the linear motion. Just mark this is a u2, this one is u2, then join this to this one, you have to join this one. Then triangle EFG represents outlet velocity triangle. Okay, outlet velocity triangle. So next, again this triangle represents the inlet velocity triangle, and this represents the outlet velocity triangle. Okay, so I hope you understood this much. Then again the next part of this video, just I'll draw this triangle once again at the inlet as well as at the outlet. Okay, again I'll continue this one. So in the next part of this video, so I'll draw this one as well as this one, but I hope understood the basic concept how to draw velocity triangle at inlet as well as at outlet.